Right, now these so-called literal equations are a fancy expression for make x the subject of an equation. So these equations do not have numerical answers. They will have equations with extra pronumerals where you would have numbers. So instead of having maybe just x and y, you might have x, y, z, and p and m. So you just solve them as normal, but you just have to mind the pronumerals. Here's one. You need to solve this equation for x, and the constraint is that p is positive. So you apply your regular log rules. This power of half goes to here, and this 5 goes as a power of 5 there. Log to the base 2 of x to the power of half minus log to the base 2 of p to the power of 5 equals log to the base 2 of 6. Then you can use the division log rule, where you can combine these into a single division with the same base. Log to the base 2 of x to the power of half over p to the power of 5 equals log to the base 2 of 6. Then because these are both to the base 2, you can make these equal each other. So x to the power of half over p to the power of 5 equals 6, which means that x to the power of half is equal to 6 times p to the power of 5. And then to get rid of that power of half, you multiply it by 2. You square it, and you get x is equal to 36 p to the power of 10. Now in this case you have an exponential equation, but because of this exponent in the denominator, we have to do this trick first, where we multiply the entire equation by e to the power of kx. Right, so how does that look? Well, if you look at this term here, e to the power of kx times e to the power of kx becomes e to the power of 2 kx. And then this term here, 3, multiplied with e to the kx becomes 3e to the kx, which leaves us with this last term here. When you multiply a over e to the kx times e to the kx, these will cancel off, so you're left with a. Then your next step is to spot the hidden quadratic. Do you see it? We have to pretend that this is g, and that gives you g squared minus 3g, g squared equals 3g plus a. So we let g equal e to the kx, and I could have chosen any other letter, I just happened to choose g there. So therefore we have g squared equals 3g plus a. And if we rewrite that in quadratic form, you have g squared minus 3g minus a equals 0. So from before we had the quadratic which is in g, and this time we can't factorize because we don't know what a is. So here we use the quadratic formula. Remember our good old quadratic formula, where what used to be x we'll call now g. Oh, that's not working. G is equal to negative b plus or minus the square root of b squared minus 4ac. I need to start it over there, but that's right, over 2a. So here a is equal to 1, b is equal to negative 3, and c is equal to negative a. So therefore g is equal to negative 3 plus or minus negative 3 squared minus 4 times 1 times negative a. You take the square root of that term there over 2 times 1. That gives you positive 3 plus or minus 9 plus 4a, all divided by 2. Now if we split that up into two parts, you will end up with e to the kx equaling 3 plus square root of 9 plus 4a over 2, And the other case, e to the kx equaling 3 minus square root of 9 plus 4a over 2. So what we had was the two cases, and hopefully you'll notice that if a is positive, then the argument in the square root bracket must be bigger than 9. And so by consequence, this term is going to be negative, and this term is going to be positive. Now, because e to the kx is always positive, then this case cannot exist, because you can't have negatives. So we only have the first case over here on the left. And the last step is to take logs and then divide by k. So let's do that. So kx is equal to log to the base e of 3 plus the square root of 9 plus 4a over 2, all in brackets. And then x is equal to 1 over k times log to the base e of 3 plus the square root of 9 plus 4a over 2.